A convenient way to handle bitumen at lower and therefore safer temperatures is to manufacture emulsions. We see this approach is used expansively already in processes such as surface dressing, microsurfacings, and to a lesser extent in cold mix technology. However, there is an increasing focus on reducing the working temperature in all aspects of the pavement construction and maintenance business, and so the use of emulsions is likely to expand over coming years. This module will look at the basics behind what an emulsion is and how it is made. We shall progress to consider how the emulsions are specified, and finally look at one or two examples of how emulsions might be used. We are all familiar with using emulsions without probably actually realising it. For example, we must all have consumed milk either on cereals, in coffee or in cooking. Milk is a great example of a naturally occurring emulsion type of material. If we look in detail at what milk actually is, we see it's a dispersion of fat globules suspended in a watery fluid. Whilst it looks like a single liquid material, it is in fact made up of two distinctly different phases. This becomes uncomfortably evident if you leave a bottle of milk out of the fridge for a few days and you witness those fat globules separating out of the watery phase. You see a distinct white solid type of product at the bottom of the bottle and a yellowy liquid on top. Of course, this separation is utilised very effectively when making cheese. So, we see that emulsions are present in the natural world. What do we do in the man-made world to artificially create emulsions? Again, the technology has been used by almost all of us in our everyday life, probably without even realising it. Believe it or not, the most common example is probably washing up after a meal. If you have a greasy plate, you can soak it in water, but the grease remains on the plate, separate from the water. As soon as you add a squirt of washing up liquid, the grease almost magically lifts off the plate and is dispersed in the water. This is very similar to the technology we use in manufacturing the bitumen emulsions. In the example of washing up, the grease on the plate is made up of an oily type of product, which is unlike the structure of water, and the two materials consequently do not mix. The molecules of washing up liquid are made up of two parts. One part that has an oily type of structure and is very similar to the grease, and therefore mixes well with it. The second part of the molecule is more like water and mixes well with water. Therefore, the grease is joined to the washing up liquid, which in turn is joined to the water, and therefore indirectly the grease mixes with the water and is carried off the plate. So, an emulsion is a dispersion of two dissimilar materials that would not normally mix. Generally, the emulsion will take on more of the characteristics of one of the phases or constituent materials. We manufacture bitumen water emulsions using exactly the same approach as the washing up example. But instead of washing up liquid, we use emulsifiers, which again have two parts to the molecule. One part like water and one part organic in nature like the bitumen. This emulsifier is dispersed in water, and then to activate the part of the molecule that is like water, we add acid. In simple terms, the bitumen is milled with the water phase containing the emulsifier, with the result that the bitumen is dispersed in very small globules surrounded by these emulsifier molecules in discrete micelles or structures. As one structure approaches another, the charged or acidified part of the emulsifier molecule repels each other and the emulsion remains stable. Okay, so let's think a little deeper about the emulsion itself. The bitumen globules form the discrete phase of the emulsion, and the water the continuous phase. It's the characteristics of the continuous phase that has the main influence on the overall behaviour of the emulsion. Having said that, the way the bitumen globules are dispersed also has an influence. Let me explain and make that a little clearer. Because the water is the continuous phase, the flow characteristics essentially are dominated by the water. Hence, at ambient temperatures, the water will want to flow. Yet the individual bitumen globules are predominantly solid in their behaviour. The overall behaviour is therefore solid globules floating and freely moving, a little like the snow globes we might have on display in our living rooms. It is also true that the size and shape of the bitumen globule will affect the rate or speed at which the globules can move past each other, and so can affect the actual viscosity of the emulsion. What this means is that we now have a high viscosity or predominantly solid bitumen able to be transported around and used at relatively low or ambient temperatures. This compares with the normal conditions we use bitumen, where in order to move bitumen around and coat aggregates, etc., we have to maintain the bitumen temperature well in excess of 100 degrees C. For some of these bitumens that have been modified with polymers, this temperature could even be as high as 190 degrees C. As well as the obvious health and safety benefits this brings in terms of reduced potential for burns, we also see benefits in reducing heating requirements, which for mobile plants is very important. So, the first challenge involved in emulsion design is to produce an emulsion with a stable dispersion of bitumen globules that can be stored and transported. The second challenge in the design is to ensure the bitumen and water are able to separate under the correct conditions to enable the bitumen to be left in a usable state. For example, in a surface dressing context, the emulsion has to remain as a stable emulsion during application so as to provide an even carpet of bitumen and also adequately adhere to the chippings. Thereafter, the aim is for the water to separate from the bitumen, so leaving the pure bitumen to do its job. Bitumen emulsions are defined according to the European specification EN 13808, which is a framework specification really classifying 4 key characteristics: bitumen content, viscosity, emulsion stability, and then the physical characteristics of the residual bitumen, which include softening point, penetration, and specifically for polymer modified bitumen, cohesion values. The description of emulsions provided in this module are all acid-based or cationic. There is also technology available to manufacture caustic-based or anionic emulsions, and indeed neutral or non-ionic emulsions. However, this module is focused solely on cationic or acid-based emulsions. The emulsions are classified or named according to a prescribed, slightly complicated nomenclature. This involves a 7-digit description of the emulsions. The first digit clarifies that the emulsion is cationic and is the letter C. Digit 2 and 3 describes the midpoint figure for the bitumen content range in percent. Digit 4 describes if the emulsion contains paving grade bitumen by including the letter B. Digit 5 describes if the emulsion contains a polymer by including the letter P. Digit 6 describes if the emulsion contains flux oils at a concentration greater than 3% by including the letter F. And finally, digit 7 describes the stability of the emulsion by quoting the class number of breaking behaviour. Emulsions are currently used in a number of applications. However, the main ones include surface dressing, microsurfacings, bond coats and tack coats, and cold mix asphalt. To summarise this module on emulsions, we have looked at what an emulsion is and that this type of structure exists in nature in many different forms. We looked here specifically at milk. We have also talked about how we can manufacture artificial emulsions, considering the role of emulsifiers and the relative contribution the continuous phase and the discrete phase make to the physical characteristics. Finally, the specification EN 13808 has been considered, along with the type of applications common to emulsions.